Hello, my name is Ryan Gregory, and today I'll be presenting on irrigation scheduling, specifically a practical and economical method to make on-farm irrigation management decisions. So this will be a simple method that people with basic agronomic experience can conduct, and is cheap and economical, and is already field proven and a practical method. So as Carrie Underwood said, so a little bit more about me. I'm currently a master's student studying crop science at Texas Tech University. I work for Dr. Jane Deaver's public cotton breeding program at Texas A&M AgriLife Research Center in Lubbock. And my thesis title is here, a visual field screening strategy for purity and seed quality in conventional breeding nurseries. So basically just developing a field screening strategy for adventitious presence of transgenic glyphosate resistance in our conventional cotton breeding nurseries. I received my bachelor's from Texas Tech as well in environmental crop and soil science in 2013, and I have already passed my certified crop advisor international and state Texas exam, and in the process of completing my application to become a full certified crop advisor. And I have numerous years of experience ranging from working on the farm since I was in junior high all the way through high school, multiple farms in Texas on mostly cotton and some corn, in Colorado with corn and wheat and sunflowers and a little bit of sorghum. I had a year internship with the Bayer Crop Science Regional Cotton Agronomist, two of them based here in Lubbock, Texas. I was a field scout for a summer with Hooten Crop Care in the High Plains region based out of Lubbock, and I worked with crops, primarily cotton, corn, sorghum, and sunflowers, and then a little bit of millet and some research plots. And I was an agronomist intern for a semester at BE Implement, which is a John Deere dealership that's based out of Brownfield, and they have multiple locations around the Lubbock area. And there I worked with mostly their Field Connect soil moisture probe, and then with their integrated solutions department with GPS and variable rate technology. And my family farms around Lorenzo, specifically my brother-in-law, and I've helped him manage the agronomic side of his farm basically since I've been in school, or real intensely the past few years. And then I've been in my master's for 2 years at Texas AgriLife Research here in Lubbock, working in the cotton breeding program. So specifically this topic will focus on the Texas High Plains, which is this region you see in blue. You see here in the blue this multi-county region, and we are here in Lubbock, which is based right here, and our farm is in Crosby County out here. And here in the High Plains we have a semi-arid climate, so it's not a full arid, but it's definitely not like East Texas where they have a pretty good subtropical climate, lots of rain. So we're mostly semi-arid, pretty dry, not very humid, but we do get some rain, and it's not 120 degrees as it is in Arizona. It's definitely heavy in crop production. There's also some ranching here as well, but lots of crop production in Lubbock and the surrounding counties. In this region is the largest contiguous patch of cotton acreage in the world. So a little bit more specifically about the climate. It's called the High Plains because it is up on the beginning of the caprock of the High Plains for the entire central US and all the way into Canada of North America. So Lubbock specifically has an elevation of 3,256 feet, and that definitely affects the growing climate here. We get cooler nights, which is beneficial because it helps our plants be able to recover in the field from the heat and water stress they accumulated throughout the day. We have a lower pest pressure, the higher elevation. We get more freeze kills in the winter, so we don't have as much specifically insect pest pressure as maybe the lower Texas and then the lower southeast delta of the United States. And we also get a limited season length. Our average freeze date is October 31st, but we've gotten freezes all the way to the beginning of October and then all the way into November. So the high elevation can limit your heat unit accumulation in some years. So that becomes a big aspect of crop management, irrigation management, is you need to manage your crop maturity. We have warm summers, so here is the monthly average graph for temperatures in Lubbock, and you can see through June all the way to August we are above. See, this is high and low averages, but the high averages are above 90 degrees for June all the way through August. So we have 90 to 100 degree days almost every day for the majority of the growing season. So we get pretty warm in the summer, but we have those cool nights, which is why you see these graphs drawn down so low. Specifically July and August, that cool nights really help us recuperate while we're flowering. And then we have a high ET. Lubbock in the High Plains is known for extremely high winds, and we're semi-arid climate, so we don't have much humidity. It's already pretty dry, so we get real high evapotranspiration rates during the growing season. And precipitation, so these blue bars are the precipitation graph, and thankfully some of our highest precipitation is during the growing season here in May and June. Well, mostly our crops are planted in May, specifically cotton is planted in May, and we have a good start. But unfortunately for the summer, July and August is our lowest average for the summer, which is when cotton is flowering. And so irrigation becomes very important in those 2 months. Our average rainfall is 19.18 inches, specifically in Lubbock. For the whole High Plains, it's typically considered an average of 18 inches. However, if you've ever been around Lubbock very long, you know there's no such thing as an average weather year on the High Plains. So usually the average is just the medium between the highs and lows that we have. It's not really a true representative of what every year looks like. And specifically, for example, in 2010 we had a good crop production year, had almost 25 inches of rainfall accumulated that year, and then the exact next year, 2011, we only had 6 inches. And this isn't just growing season, this is the total year. And so the average of those two is pretty well in the median here. It's going to be a little less than 19 inches maybe, but it's still pretty close. And so that shows you that the average doesn't mean that's what we see every year. We're typically having swings, real high, good wet years, and then drought years, and hopefully we're pulling out of a 3 to 4 year drought now this year. We'll get some good moisture. So the crops, as I mentioned earlier, primarily is cotton. Over here is a cotton field that's opening up, and here's a cotton boll. We call these the money bowls because they've got 5 locks instead of typically 4 locks, so they're a little bit bigger bowl, and so we just like to call those money bowls. But on a whole, the High Plains is usually a 60% dry land acre average, which is surprising because of the semi-arid climate. And that's going to be planted acreage. The harvested acreage, and definitely not the bale production, is 60% dry land, but planted acreage is typically a 60% average, and that's been pretty static for several years. And the remaining 40% is irrigated acreage, obviously, but of that we have about 60 to 70% of that is marginal irrigation, or what I'm terming supplemental irrigation, which means that irrigation does not have the capacity to fully meet the requirements of the crop during the season. So we have to become really good at managing our irrigation and try to use it when it really counts, because we don't have unlimited irrigation in very many situations. So center pivot and drip is the most common. There used to be lots of surface, row water, and flooding, but with our new technologies and learning about water use efficiency and such, we have gotten away from that quite a bit. We have really good adoption of drip in this region. We've had drip here for 20 years in some places, and there's still more acreage converted every year. The drip does really well out here. We have lots of center pivots. Here's a photo I actually took just east of Lubbock out of an airplane myself, and you can see all the circles of all the pivots that we have, and other areas it's even more concentrated. And you see a patch like this that's split up and looks like it has good vegetation. That is a drip field right there. And our irrigation source is the Ogallala Aquifer, which covers I think it's the largest aquifer, I believe, for the United States, and it's here. It's also referred to as a high plains aquifer because it covers all over the high plains from South Dakota all the way into central Texas. But the issue, especially with this southern break below Kansas or below Nebraska even, is the aquifer has been depleting ever since it's been tapped into in the, say, 40s and 50s to begin irrigation. We don't have very much recharge, especially not near as quickly as we have extraction. So the aquifer is definitely depleting in this graph over here on the right. The darker the color, the darker the red, the more the aquifer has depleted since 1998. And so in Lubbock, specifically the county, it's not too bad. There's some yellow fringe and some green, still is some depletion. But you get over into northern Crosby and Floyd, it's definitely got some depletion. And then in Palmer and Castro County, where they grow lots of corn and lots of year-round crops for silage for dairies and feedlots and such, they have had extreme decline of their aquifer, and they're switching over to a lot more water use efficient crops such as cotton than corn. And the same up here in the northern part of the panhandle, where you see really bad depletion. The crops such as cotton are starting to move a lot further north, just specifically for this depletion of water resources. And so, as I said earlier, we are primarily in a irrigation supplemental irrigation situation where we are having to combine the irrigation with rainfall to try to meet the needs of the crop. And most of the time, once we hit peak water demand, we are still not going to be able to meet that full needs. So we're just trying to supplement as much of the need as we can. Because we don't have as much unlimited water as we'd like to just water the crop as much as we want or as much as it needs. So because of that, irrigation management, specifically very intense irrigation management, is a must. Because with a supplemental irrigation situation, timing is key. The amounts are crucial. You can make or break a farm just based off of one or two key irrigation decisions you make in a year. So irrigation management, there's lots of education and research going on in this area, specifically on irrigation management, because it's such a key for our region. So the main keys to irrigation management I'm going to discuss today is, number one, know your crop. You need to know what's going on in the field. You need to know how it grows. You need to know the critical stages, its water use. And you need to know the field as well, the field that crop is going in, the soil types that are there, so you can be prepared to go into it fully knowing what to expect, how the crop will perform, and how it'll behave in that specific field. You want to know your irrigation system. You want to know what you're working with, what kind of pumping capacity on the wells you have, what kind of efficiency that system is going to have in terms of supplying water actually to the plant roots, and the overall operational capabilities. What all options do you have to do with that system? And you want to know your current moisture status is extremely critical, because if you don't know what kind of moisture you have, you don't know what kind of moisture the plant needs or how much more it'll need. And so within that, ET rates are very important, assessing the soil moisture throughout the growing season, and also looking at the weather forecast of what you think future ET may be, and if maybe you're going to get some precipitation or not. And then finally, once you have all of this knowledge, you're going to bring all of that together to make your irrigation decision. And this is a very critical step, and you do not want to make your irrigation decision until you have done due diligence to all of these areas here, and you feel like you have adequate information to make a confident decision, because there is no easy button. This takes lots of experience, lots of effort, and there's no undo button. Once you've put that water out, or once you haven't put that water out, there's no turning the timetable back. There's no pumping that water back into the aquifer. It's a one-time decision. There's no undo button, so you always want to make sure you're fully prepared to make the best possible decision. So knowing your crop, specifically I want to talk about cotton. Knowing your crop, you want to know the growth. You want to know the key growth stages, and at what growth stages, average estimate of what the root depth may be. Rooting depth is something that's real difficult to measure, and you can't really see because it's below ground. So you want to just try to have an average idea of what root depth with what critical growth stages. It's because the roots obviously is where the plant is pulling its water from, so you'd like to know how much water it has access to. You want to know specific patterns of growth, such as an indeterminate pattern of growth like cotton, or a determinate pattern of corn, so you can know how do you want to manage its growth, and how can you water play into how the overall growth habit may be of the plant. You need to know water requirements, which really go back to the growth stages and the root depth. At what time of the year, a specific stage, how much water is that plant needing then? And so you want to know water use curves of your crop well. What critical stages, like corn tasseling, is extremely critical. You want to make sure no water stress at tasseling, because you're going to limit your yield right there. And then the water use efficiency, how efficient is this crop with the water it receives. And then resilience, how much stress can the plant take before it really starts to have a yield dock, or can you use stress to your benefit, or is stress a zero tolerance policy? Evapotranspiration, that is very key in knowing your crop. You want to know how much is that plant going to transpire, what is the evapotranspiration in that field with the crop. Now this is something no one can master. It's extremely difficult. It's its own discipline of research, just crop water use efficiency. People have devoted their entire careers to studying this. And so don't go into this thinking you're going to know everything, but you want to try to learn as much as you can and really tailor it to your specific experience. And lots of research studies and publications, so you can look up tons of information and learn about it. The Food and Agriculture Organization of the United Nations has really good sources. They have crop water use in terms in respect to evapotranspiration, and they have there's tons of information on the water use efficiency of all types of crops. And specifically something they work on that becomes extremely beneficial, and what I'll discuss specifically today and utilizing for irrigation management, is a single crop water coefficient, or reference ET versus crop ET. And basically when you see a ET station, they're going to be monitoring a specific type of plant. Typically it's a well watered area of grass, and they will use that to estimate how much evaporation and transpiration is coming, how much evaporation is coming from the soil, and how much transpiration is coming from that grass crop. And then they research how does that grass crop compare to corn, to cotton, to sorghum, to soybeans, and they see how the transpiration rates throughout the season differ, and so then they develop this crop water coefficient. So once you know in a specific area a true measurement of what a reference ET of, say, a reference grass crop is, and you know your corn at this stage uses 1.2 times the amount of water than the reference grass, that's where you get this KC value, where the corn, whatever that your ET0 or ET0 is what you'll hear it referred to as, of the reference crop, you multiply that by 1.2, and then you know how much moisture your specific crop you're looking at is using. So ET, more specifically, no, not the alien, but we're talking about crop evapotranspiration. ET is an excellent way to determine crop water demand and use, because it is the measurement and prediction of total crop water use. It is a measurement of how much moisture is being lost through evaporation out of the soil, and how much the plant is transpiring through its stomates, through stomata. The only water use that you wouldn't see in this would be some type of deep soil drainage or runoff, but basically whatever water is in the soil in the root zone is either going to be evaporated or transpired. So ET is a great way to measure crop water use. This is, I believe, the irrigation tool you should be using, and especially in this area as we're trying to go to more intense irrigation management to better utilize the limited amount of irrigation we have. There's lots of research and lots of trainings going on in the region, specifically from the Texas Alliance for Water Conservation, trying to train producers into how to use ET for irrigation decisions. It's a true calculation, as I mentioned before, on a reference crop. It's not just a mathematical function. They are actually using environmental parameters such as temperature, wind speed, humidity, soil moisture. They're using all of these things, radiation levels, to determine an exact amount, a true amount of how much water is being evaporated and transpired in that environment. And there are many great sources to measure this. The National Weather Service or just your local weather station probably has enough data for you to calculate this. And specifically in our region, we have the West Texas Mesonet, which I've heard many people refer to as one of the best weather station networks in the United States, if not the world. And this, I couldn't even fit all of it into a page, but here, all these stars are different Mesonet stations where they're collecting data, and they have the specific sites you can go to where this data is translated into evaporation, transpiration data for you. And as you can see, there's just sites scattered all over the region. Specifically, our farm is in Lorenzo, which is between Lubbock and Rawls, so we typically use this Rawls Mesonet data or the Lubbock Mesonet data, depending on which farm we're at. And the Texas ET network is what I specifically use because you'll see that here it is right here, and because they already have it all labeled out for you, they run the calculations and they just put it into a spreadsheet. You can go straight to there and just look at it specifically for each day, the measured amount of reference ET, the environmental data they use to calculate that, and then a past week summary. And then they also have these tools where you can click on home watering, turf or landscape, or crop irrigation, and then it'll take you to then a decision tool where you can enter your irrigation information to help you decide how much irrigation you may need. Okay, knowing your field soil type is the first thing you want to know, and that's because the soil is where the water is for the plant. So you want to know as much as you can about the soil. You want to know the soil texture, because that's going to influence how much water that soil can hold. You're going to want to know your slope. Here's our field that I'll be doing on-site irrigation management later on in this presentation, and it's as you can see, it's a Pac-Man pivot. It bounces and then reverses around here because we have a low ply lake wetlands area, and so we don't want to make a full circle, so we'll bounce around there. And up here towards the road, it is more of a flat, and then we have a slope on either side of that going down towards the low level ply lake. And so that greatly affects how the water in irrigation is going to behave on this farm. It'll pull up pretty well here and have good infiltration speed. On the slopes, it's going to have quite a bit quicker runoff, and it's going to take a little longer, and you're going to have less infiltration into the soil just because the water is going to want to be running off down the slope. You want to know your field history, what type of crops has it produced in the past, how well did those crops produce, any type of diseases or weeds or low spots where water may pool up, or just any history you have, is the more the better, because that'll help you understand things in the future and prepare. You want to know the general climate. I showed earlier, I showed the average temperatures and rains and the precipitation levels for Lubbock, and this is farm's pretty close to Lubbock, so that's its kind of general climate. You want to know agronomics. What's your yield goal for this field? How much do you think this can produce, because that's going to determine how much irrigation you're going to want. How are you managing this? Is it a full tillage, limited tillage, no-till? What type of rotations? And what inputs, what type of nutrients are you going to have? What type of PGRs, plant growth regulators, are you going to use? You want to know what inputs. And Web Soil Survey is a great source, and here's the link, and that's where I pulled this this image from. It has really good satellite imagery, and it also is like the old soil survey books that you used to see, but it's all on the internet now, and you can pull up soil data and soil maps for really anywhere in the United States, and most of the time they're fairly accurate, especially if your field is close to a major road. It's going to be really accurate, and that gives you really good data on the soil type and tons of other information. So here's the Web Soil Survey website, and you go there and you'll just click on this green button and it'll take you in, and then you just zoom into the area you want, and then set that area, and they'll pull up all the information for you. Alright, now that you know your field and your crop, you need to know what kind of irrigation system you're working with. What type? Is it a center pivot? Is it a subsurface drip? Or is it going to be surface water or row water? And that'll help you determine the efficiency. Efficiency is going to be based off of type, and then within each type you can have different setups like LISA and LIPA. So here is some water efficiency study, and it has field and farm efficiency. We'll look specifically just at the field efficiency. Average for a furrow irrigation, 65%. So that's a lot of wasted water. 35% of whatever you're pumping is being wasted, and the plant doesn't even have a chance to use that. Once you get to a center pivot, it increases quite a bit. And basically, as technology has progressed, the efficiency has progressed as well. The impact heads, which would be what people would call wobblers probably, that kind of just sprinkle the water in the air. This study came with an average efficiency of 80%. In West Texas, those wobblers are used for peanut production a lot to try to keep the humidity up. And if your irrigation system's increasing field humidity, you know that means you have lots of evaporation. So in our hot and windy climate, I would expect this efficiency to actually be quite a bit less than 80% because we have so much evaporation. Now spray heads would be like a pad that shoots the spray lines of water out, or LISA, low elevation spray application. Those are going to have about 90% of efficiency, and we see quite a bit of those here, and a lot of the research was developed here. And then LIPA, or low energy precision application, is going to be drag hoses, and more commonly now you see people using what they call bubblers or a splash pad, and those have high efficiency as well, 90 to 95% efficiency. And then all the way down to subsurface drip, they're estimating 90% efficiency. I'm not sure on exactly how this study was conducted, but I would assume that you can definitely, it shows here a range of attainable 95%. I would think in most cases in our region we're more towards the 95% range. The drip systems work very well here. So once you know your type of irrigation and your efficiency, you want to know pumping capacity. This is probably the most important calculation you can do, is gallons per minutes per acre. How much water do I have available for this field? So if you have a 120 acre quarter section pivot and you're pumping 300 gallons per minute, then that means you're going to have probably 2.75, 2.6, anywhere in there of gallons per minute per acre. You don't want to just know, you can have a well that pumps 1,000 gallons a minute, and that's great, that's a very excellent well. But if you're trying to put that out on 2,000 acres, that's only half a gallon an acre. You need to know how much gallons per minute per acre, so you know how much water you have per area, or how much water you have for those plants you have in the field. Then you want to understand your system capabilities. Is the pivot programmable? Will you be able to put specific speeds and programs in there so the pivot can you can have irrigation programs in there where it may speed up in a low spot that you don't want to water as much, and then slow down somewhere where you like to water some more? Does it have option for variable rate programs? That's a new technology. It's been real beneficial, so you can tailor specific irrigation treatments to your field. Drip controllers, you can adjust which zones to kick on when and for how long and how much water you want to put out in those zones. And do you have wireless capabilities? Can you start and stop your wells and irrigation system through the internet or through your cell phone? So that's going to affect how you manage your irrigation. And you want to know the history, how well has this system performed in the past, how good have the wells done. Something you see in this region a lot is you say you pick up a new piece of land, and you go out there and you kick on your wells for the first time, and you're getting 600 gallons a minute right there at the center pivot, and you think, oh, that's great, and so you try to really manage your farm off 600 gallons a minute. But we have that depletion. By the end of the year you may be only pumping 450, and you don't have near as much irrigation capacity as you began with. So it's really important to know the history of how the wells perform over the season. How old is the system or the wells? Can you expect to have issues throughout the year? If you're still using turbines, are your turbines pretty good, or are they going to break down and you have to make some irrigation decisions and repairs? So history is important as well. Assessing field soil moisture. You want to determine the soil moisture content currently in the field throughout the season. Before you start the season, at the end of the season, that's going to help determine everything. How much you want to irrigate, if you want to irrigate at all, when you should stop irrigating to prepare the crop for harvest, when you should start irrigating in the beginning of the season. And there is so much technology for us nowadays, neutron probes, capacitance probes, so many ways to measure real-time soil moisture. In my humble opinion, there's no need to get fancy, because you can only, especially in our region, there's only so much you can do with your irrigation. It's nice to know all the different depths of specific soil moisture, but you can't necessarily affect how much moisture you have 4 feet deep without affecting how much moisture you have towards the surface. So I think the simpler the better. Lots of that technology costs money, which might negate the increased yields or the increased water savings you get from more precise irrigation. And then it requires time, which is money, and training, which is money. Not everyone can just go pick up a neutron probe and start reading soil moisture levels with that. It takes lots of training and time to become experienced. So I like to stick with the simple methods that are practical, reliable, efficient. You can do these quick, cheap, and easy. Soil moisture by feel is a common one. I don't have as much experience with it. Dr. Glenn Ritchie, crop physiology professor at Texas Tech, he talks about how he's used this in his consulting experience. And really you just use a soil core probe like you would taking soil nutrient samples, and you just pull that core out, and then you can just kind of texture that soil in your hand, and just based off its visual looks and based off how it feels, estimate how much moisture is in the soil. Now that's going to require some training as well, just so you can get experience of making accurate moisture calls, but it's still going to be pretty quick and cheap. I have one of these probes here, and it costs about $70. Soil moisture rod probe is what I like to use, and that's just a steel rod with a blunt tip on the end, and these are designed to where they can penetrate anything equal to or greater than 75% field capacity typically. And so these are extremely simple. All you do is go out to where you want to check the moisture and just push it in with your hand as far as you can, and once it stops, that means it's hit a dry layer that's going to be less than 75% field capacity. That's typically what it takes for one of these probes to penetrate. And so then you can just estimate what depth of soil has adequate moisture for the crop, and based off your soil texture you can determine how much of that water is available to plants and at what depth is your roots. And these are used extensively. Most consultants I know, and the consultants I worked for at Hooten Crop Care, they use this soil rod probe. So they're very common, very well known, and trusted in this area. As I mentioned, once you have your moisture reading, you'll use your soil type to determine plant available water, or PAW. How much of that moisture can the plants actually use for their benefit? And finally, making your irrigation decision. This is where the money is at. This is what consultants are paid for. This is where the research is going. This is where your yield is made or lost, is based off your irrigation decision. It's extremely critical, so you want to take your time, be thorough and precise. So as I mentioned earlier, no going back, no undo button. Once you make that decision and pump that water or choose not to pump that water, then it's all in the past. You can't go back and do that decision over again. Better luck next year. But thankfully, as there's been more and more research going into this, and this has been studied for such a long time, there are many tools available, tons of online resources now. But I think simple math is the best tool. Basically, you're just looking at inputs and outputs. You know how much your crop is using. You know how much the ET is taken away. You know how much is in the soil. So then you can just do a simple difference calculation, and then you know the water requirement, and you know how much you can put out with your irrigation system. So then you determine the best way to cover the difference between the water use and the soil water content with your irrigation system. So really, I think simple math is the key. Self-designed tools work really well. Later on I'll discuss an Excel program I built for myself that we use for irrigation management decisions. Here on the right is the Texas Alliance for Water Conservation. They have an irrigation calculator, and you just enter your gallons per minute you pump, your acres, how much inches, and it'll tell you if you want to make a 1.2 inch application on your field, how long you should run that system. And so there's lots of tools out there that can help you. Alright, so now let's begin with the real world example of irrigation management, and this is going to be with a field that is on my brother-in-law's farm that I've been working with for several years. And so first, knowing our crop. Our crop is primarily cotton. The growth of that crop is indeterminate, which means we will have vegetative and reproductive growth ongoing at the same time throughout the season. The crop water use, I've been around cotton ever since I was born. My whole life I've been around cotton farming, so I know the growth stages pretty well. And I use the FAO crop coefficients to determine the crop water use off of ET, as I mentioned earlier. And so here it is broken down into growth stages. And here's the crop coefficient. At first bloom, it'll be using 0.44 or 44% of what your reference grass crop ET would be using. Once you hit max bloom and first open boll, when you're blooming and boll filling, that's when you are using lots of water, and you'll be using even 110% or 1.1 of that reference ET. And we just have a general idea of the rooting depth of cotton. We know our soil around here. Lots of soils can have restrictive calcium layers. Thankfully, on this field we'll look at specifically, it has pretty good soil for good rooting depth. And once the cotton really gets established and is blooming, I'm gonna estimate it's probably got a 3-foot of root depth. But really, for most crops, your effective root depth is 50% of your moisture, or I'm sorry, the majority, like 80% or more of your moisture is being taken up in the top 50% of your roots. So really, the top foot and foot and a half is really critical for cotton water use, even though it is a taproot that goes deep. And stress can be good and bad for cotton. Like I said, it has an indeterminate growth, so sometimes it needs a little stress to kind of force that cotton more into reproduction instead of vegetative growth. It's a perennial plant that we crop as an annual, so it's going to want to really grow, so you might have to hold back on its water a little bit to keep it from getting too vegetative, especially to keep it from maturing too late. And it can also be bad. Once you get too high levels of stress, you're really going to limit your yield, and especially once you hit first square all the way to first open boll, you're going to be limiting and dropping squares. Where it becomes extremely crucial is around first open boll. Until a boll is 5 days old, it has an extremely high chance of being aborted by the plant. If it gets any stress in the region of that boll, the plant is most likely going to abort. Once it's about 5 to 7 days old, that boll is probably stuck on there. So during fruiting, you really want to try to avoid stress. Now, stress onset is usually, I'm sorry, here it says plant available water. I meant it's field capacity. 55% of field capacity is typically when you're going to start to see yield limiting stress or plant stress accumulation. Now, this is not permanent wilting point, but you don't want to hit permanent wilting point, because that's when you've stressed the plant so heavily it cannot recover even when adequate moisture is available. So typically 55% field capacity is where I'm going to shoot. I want to try to stay above that to try to limit the stress as much as possible. Then we have lots of history for this farm. Our APH, or average production history, is now up to 1,000 pounds of lint per acre. It has good fertility. We do have disease issues in the field, especially verticillium wilt, which is can be increased with a thick canopy, moist soil. So our irrigation decisions and our disease pressure really affects our irrigation decisions. And this field still has some weed issues we're working on, so we will have weed competition, which is going to take away from our crop water. And as I mentioned earlier, here's a graphical representation of the water use of cotton over time. And obviously it starts out low at the beginning of the plant, and then it really starts to increase once it starts blooming, and peaks out about the beginning of bulb opening, and then rapidly drops off to maturation. Alright, knowing our field, we know this field extremely well. It's been in my family for 2 generations. My family's owned it even before I was born. It's on the Texas South Plains, so that describes the climate we're dealing with. It's a 100-acre Pac-Man T&L hydraulic center pivot. It's that pivot I showed you in an image earlier that makes that Pac-Man shape around that low spot. And it has 3 gallons per acre irrigation capacity. And it has those slope issues, which becomes a huge challenge in our irrigation management, and I'll get more specifically into that later on. And overall, it has a clay loam soil, so which has good water holding capacity, but it's also going to have a higher end permanent wilting point, because that clay is going to hold the moisture so tightly. And so we're really going to target to stay above 55% field capacity to limit stress as much as possible. And over here is just average per foot of soil, how much water can a silty clay loam hold, in 1.8 to 2 inches per foot. And so once we know our rooting depth and we know how much moisture is there, if it's a 100% field capacity, you're going to have 1.8 to 2 inches. So if we're shooting for 55% field capacity, we're going to want to stay 0.75 inches, 0.8 inches of water per foot of soil, 0.1 inch or 1 inch. And here's just a representation of permanent wilting points. Permanent wilting point is below the red. There's no available water, and this brown is when stress is possible. So we really want to shoot for this orange layer here, because above that is whenever you have saturation and lots of free water, so really wasted water, and you can also get some hypoxia with limited oxygen to the roots. So this is really the region we're going to shoot for. So here's the soil map from Web Soil Survey I mentioned earlier, and there's several soil types here as it slopes down into this low spot, but primarily PUA, PMB, ZMA. See here, you can see 46% is Pullman silty clay loam. Not the other 9.4 is a Portalis loam. 27% Pullman silty clay loam with more of a slope. So you can see 27% of ours has 1 to 3% slope, and that's going to affect our irrigation. Then Randall clay, which that's mostly here, which that's not cropland, so we can ignore that. So most of the is a silty clay loam soil. Knowing our system, as I mentioned, it's a T&L hydraulic pivot. It has 100 acres under the pivot. It's got slope issues. We have recently gone from drag hoses to bubblers, so both of those are low energy precision application, but we switched to the bubblers, which I'll show you a video of that later. But essentially that's mostly just kind of dropping the water right in place, whereas the drag hoses direct it out through essentially a garden hose, and that water is more concentrated and has more kinetic energy when it hits the soil, and increases its potential for runoff. So because of our slope, our runoff was becoming really bad, so we switched these bubblers to try to limit the amount of energy that water has when it hits the soil and reduce that runoff, and that's worked well for us. We have here you can see the drop nozzles. They're every 80 inches, and we're on a 40-inch row spacing, so every other middle or every other row is going to be a wet row where irrigation is being delivered to the crop. We will flip those bubbler pads over to low elevation spray application or spray pads to pre-water, so we can try to get a solid consistent moisture level across the field. And it's an older hydraulic model. It's non-programmable. The only way to adjust the pivot is to manually go to the end tower and change the speed it up or slow it down. So we can't put any specific programs on it. So that limits our options a little bit. And it's got 2 submersible electric wells, and each well contributes about 50% of the water. And when they're going to start out probably 350 gallons at the beginning of the year and eventually drop off to 300. So each well is running 175 down to 150 gallons a minute. And we have this pivot. Recently we had to nozzle it down from 360 to 300 gallons per minute because of the aquifer depletion, and we're losing pressure. So 300 gallons per minute is usually what we have, which is going to translate to 3 gallons per acre in our field.
So here's the nozzle package we have for our sprinkler. Up at the top is the nozzle connected to the cage with the bubbler and pad combo below. Here's the bubbler attachment, and we flip it over to pads. We usually do that at the beginning of the season just so we can get a spray application of pre-water and just get a uniform moisture content all the way across the beds. And just here's a picture of how those pads work. It is water comes out of that tip and just shoots out and those jets. And here's some more. We just call it a spray head, or it's a pivot pad. And here's going to be here's a video. I just have a video of a bubbler as well, of the pads versus the bubbler. But there's just the spray application. Now, if you flip it over, you have this red cup, and that's the bubbler pattern where the nozzle shoots in and it bubbles out, as you see here in this video. And that's going to concentrate the water in the row, but it's also not spraying, and it's not spraying it to reduce evaporation, but it's also not concentrating it in a drag hose you'll see in a second. So we just like to use these because it reduces our runoff, but we're still concentrating that water efficiently in the row with the LIPA system. So here you can see it in grain sorghum, and this nice trickle straight down. And so see, here's the drag hoses, and it comes all the way down to a hose in the ground, which works well, except for on this farm we have those slopes and we have bad runoffs, so we like to use these bubblers. Another thing we like to do to help reduce the runoff on this field, especially in the slope region, is run dammer dikers, as you see attached here to our cultivator. You'll hear them referred to as furrow dikers or dammer dikers, and we run them in the soft middles where the irrigation is running. And here's a setup, another setup, and it just runs, and that diker grabs a hold of that dirt, as you see in this video, and just flips over it and builds like a mini dam. And you saw in those previous pictures of the drag hose and the bubbler where the water was pooling up, and that's in these little pools or small little ponds that these dammer dikers make by building up that soil, as you see. And so whenever the water runs down, it'll concentrate it there, so it allows it to soak in. As you can see in here, the water's still there soaking in. It didn't run off in the slick rows, and that's how we can slow our runoff down as well.
Alright, so now let's go to the field where I can show you more in-depth information on our irrigation system, and then a demonstration of how to assess the soil moisture content in the field.
So the next thing you need to know after you understand your irrigation system and your water source, what kind of water availability you have, and you understand your crop and your crop water use, you need to come to the field and assess your moisture situation, so then you can begin to make your irrigation recommendations. And as the title of this project is, it's an extremely practical and true method that's done in the field. This is the way I did an irrigation management checking on this farm for the past 2 years, and it's also what I did when I worked for a consultant. And it's also extremely cheap that anyone can do. The only expenses are going to be in these 2 tools I'm about to show you. But first, you want to come out into the field. You can see there's the pivot, there's the turn. You want to come out. You don't want to get close to the edge. You want to be somewhere where it's going to be a consistent spot. You don't want to pick a bad spot. Right now, we're assessing the pre-water situation because moisture pad is going to be from rain or whatever's left over in the profile from last year. So the first tool, which I don't use this one as much, but Dr. Ritchie talks about how he used to use it, and this is just a soil probe. And like I said, you know, there's lots of newer, fancier tools like capacitance probes, you know, digital, actual moisture readings, but this is extremely common method, and it's extremely cheap. I got these two probes here. They're probably $70 each. And so this is a 4-foot soil core probe. You can use this probe to take a core sample from the soil, and then you can go in and you can use the oven dry method to calculate exactly how much moisture is by weight, but that's going to take more time, and it's not going to be practical for checking multiple fields or doing the irrigation recommendations where you need a more immediate response, or you're here at the field, you want to adjust your pivot or your irrigation strategy right away. So you then, for that, what's more common and more practical would be the soil moisture by feel method, which I personally am not trained in yet. It takes quite a while of experience to get used to that, but Dr. Ritchie has past experience with that. And so you're going to want to check the moisture in the row where the water is coming from the irrigation. And you don't want to check right in the center, but maybe right the bed. Here's the bottom. I'm standing in the bottom with this foot. Here's a peak of bed with my right foot. You're going to want to check on the side. And you want to scrape the free dirt away so you don't have that free dirt, but then you have where you have the packed soil ground. And that's where you're going to begin to check your moisture. You're mostly going to want to check here on the irrigation source of the row, because that's going to be where your roots are concentrated, and no matter how hard you try, you can't necessarily control what goes on in this row, but you can assess your moisture here. And so what you would do with this probe is, like I showed earlier, you're going to want to kick away the free soil and then set the probe directly where you want to go. And this is pivot, so you don't have to be worried. If you're checking a drip field, you want to make sure you're away from the tape, you won't hit the tape. Then you're just going to push all the way in, probably the top 6 inches or so. So see, I drove it in with my hand about 6 inches. Pull out, and then you have a core. And here, from this core, you can pull that soil out. Sometimes you need a tool or a knife or something. Screwdriver. You can pull the soil out from your core. Then begin to work it and just kind of feel it and check it and be able to base the moisture off of that. Now there's advantages and disadvantages to this method. Both of these methods I'm going to show you are simple and easy. An advantage of this one is you can actually pull out the actual soil. You can do more precise measurements like the oven dry method, as I said. You also get to truly look at the soil and feel the soil. But disadvantages, it's going to be real hard to go deep, and you're only going to be checking your top moisture. And if you're not trained well, it can be inaccurate. So on a regular pivot, normally what you're going to want to do is usually check 2 places, and that's going to be a ways behind a sprinkler where you've already passed saturation, or you've already drained to field capacity, so you don't want it to be muddy, but make sure that free water's drained, and check there. And then also check about halfway across the field from the pivot, so you know you don't want to check. You can check directly in front to see how dry it is in front of the pivot, but you also want to know your average moisture, how long it's lasting. So maybe halfway away from the pivot is usually where we check. So then usually every time you check the field, you want to alternate your areas, and you want to pick a consistent spot. So on a consistent pivot, 2 places to assess the newest moisture and the depleted moisture is fine. On this pivot, however, since it's non-consistent, you know, we have the slope and then we have the flat left top. You're going to want to check probably 3 moisture areas to assess your 2 slopes and up on the flat top. So then if you need to come in and adjust or anything, and this pivot doesn't have a program on it or anything, and it's a hydraulic pivot, so there's no center panel. The only way to adjust is by adjusting the speed of your power. So there's not as much options as you can do, but on another method is just a soil probe. See, it's just a single steel rod, the handle, steel rod, and then the probe tip. The probe tip right here that's going to penetrate the soil. So with this one, the benefits of this is extremely easy, it's extremely quick, reliable and consistent, and it's easy to carry around. You don't have to have much training or anything. The negatives is you're not going to get an actual soil sample, and you're actually not going to be retrieving soil to really check the moisture content. You're just going to be kind of estimating. A consultant I worked for that's well known around here and well respected, his name is John Hooten. He's a tech graduate in agronomy, and this is what he uses to check all of his acres. And the idea behind this is it's going to take about 80 to 85% soil moisture for this probe right here to be able to penetrate through the surface. So if it won't penetrate, it means there's less than 85% moisture. So that's another disadvantage. You can't check, you want to say above 50 to 60% field capacity to avoid stress, but anything below 85% you're not going to be able to check. So this is just going to estimate how much of the soil you have 85% moisture. So just as you did with the pass probe, you just want to take away loose dirt close to the side of the bed where the moisture is coming from. Then you just put the tip of the probe in. This is a 6-foot probe, and grab the handle right here and just push in as far as you can, and you try to want to push it in as straight as possible. And then you don't need a hammer or anything, you just want to push it as hard as you can until you can't force it through the soil anymore. And that's going to be where it's hit the dry layer, where it's less than probably 80% field capacity. And so you can see I drove it in as far as I could, grip it at the soil surface, pull it all the way out, then measure it. See, here's the hand to measure. I would say it has probably 1 3/4 of a probe. That means we're going to have about 80 to 85% moisture in our top 1 3/4 or 20 inches or so, and that is where, below that is where our profile starts to dry out some. So right now this is just a pre-water situation. So I'm on the cotton that we're going to be growing here, I'm going to typically want to start out with more like a 2.5 to 3 foot profile. So once we get that cotton going, it'll have access to moisture. We want to make sure we keep the top wet till the cotton gets going, and we want to train those roots down to at least keep probably 3 foot of moisture. Once we get closer to planting, we're going to want to maybe kick the pivot on and make sure we got good top moisture to get the cotton out of the ground. And also make sure we approach about a 3 foot probe is at least where I like to start.
Okay, so here we're looking at the Excel spreadsheet I built as a irrigation management tool. And so after we go into the field and we get our soil moisture data, I'm going to record that and then come back in and open up this Excel spreadsheet, and this is where we're going to look at a comprehensive look at just our moisture situation as a whole, and then just go ahead and make our irrigation decision. And so if you had a iPad or a laptop or anything, you could take this with you in the field. So we're going to focus mostly on this area over here. And so I set this up as here you have a drop down, and this is set up to work, can really work with any field. And so first we'll pick your gallons per acre, and as I mentioned earlier, this that field we just looked at and checked the moisture data, it has a 300 gallon per minute capacity and a 100-acre field, so it's 3 gallons per acre. And here just some formulas that tells us our max capacity of how much we can deliver as an acre inch per day. If we made a 1-day circle, we would put out 0.158 inches per acre, and then if we made a week circle, it'd be 1.11 inches in a week. Then farm, you just put the name. This farm is called Lee's. So there we have the farm, and then it automatically reports the date you log in. And then here I have the drop down list of crops, and corn, cotton and sorghum are the primary crops that we would be interested in, especially for irrigation. And this year we're going to be planting cotton, so I'll select cotton. And then here is where it pulls in the potential evapotranspiration. And instead of me just having to manually go online and look up the reference ET for the past week, what I've done is created a link on this sheet 2 that goes to the network I like to use, which is the Texas ET network, which you can see right here is the website that I use, the Texas ET network put on by Texas A&M AgriLife Extension, and it's basically just like the West Texas Mesonet I mentioned earlier. And here are all the different regions. It has the stations, and I have it linked to the Lubbock station, so whenever I open that Excel file, it automatically links to this website on the internet and updates the potential evapotranspiration data from Lubbock. And for some reason the Lubbock site is down today, so we'll use this site as a reference. So once you go to the site, here it shows you the past 7 days, and then it shows you all of the weather parameters they measured, the radiation, the humidity, the maximum and minimum temperatures, the amount of rainfall, and then total wind. And then the total wind at whenever they took the readings at 4 a.m. and 4 p.m. And then they use all that to calculate this reference ET based off of their grass crop, and then they report it in a weekly summary or a 7-day summary. And so this is where we're pulling in that ET. So I have it linked to this page, so whenever I open up this Excel file, it automatically pulls that value into the 7-day PET right here. And then here I have the growth stage with the crop coefficients linked, those FAO crop coefficients I mentioned earlier, which helps you calculate your crop ET based off your reference ET. So if I went in here and I picked corn, that would change my options I had here. See, 4-leaf all the way to milk, dough, dent stage. So once I go to cotton, it'll change that back again, and seedling, first square, first bloom, max bloom. So today, since the evapotranspiration is low and we don't even have a crop in the field, let's say if I was doing this off today, then right here it's based off of feet. So we estimated 1.75 feet of moisture, or I'm sorry, that was the undo. Okay, I'm sorry. So if we're gonna work on this today, then I would come down here to my soil moisture probe and I'd enter 1.75, and that's where I'd enter my probe data. That's how much moisture we have out in the field. But since I want to show this as a in-season irrigation tool, we're gonna just do a hypothetical run. And so what I did is I've looked up historical ET data for the month of June here in Lubbock, and then found out what the average weekly ET is, and that's the average weekly ET in June for this area is 1.93 inches of evapotranspiration per week. So let's say, so we're going to run this as a hypothetical as it is in June. So this date would be see 6-15-15, and cotton is our crop. We're on Lee's pivot. The PET for this past week was 1.93 inches. Our growth stage on the 15th of June in cotton will probably still be squaring, so in the first square stage. And so then that automatically right here updates our crop coefficient to 0.22 right here. So that updated our crop coefficient right here to 0.22. So that means that cotton, this stage of first square, is going to be using 22% of the reference grass crop ET. So then here it calculates automatically for us our total water use by taking the reference ET times the crop coefficient. So it's telling us over the past 7 days that cotton is most likely evapotranspirated 0.43 inches of water based off of what the environmental conditions were. And let's say we came in and we had a 3-foot probe. So then that's where I'll enter my probe data once I've checked the moisture in the field. So I had a 3-foot probe, and we're going to estimate we had a rooting depth of 2.5 feet at that time. And so then what it's going to do is calculate the total available water content. And so this is where it's gotten a little bit more complicated. So see here we have adequate moisture available to the crop all the way down to 3 feet, but the roots are only 2.5 feet long. And so that's why I have it set up to whichever one of these numbers is the lowest. If your roots are shorter than your probes, then your roots will be your limiting water available fraction. If your probe, if it dries out before the bottom of the taproot, then your probe will be your limiting availability. So see here, if I said the probe was 2 foot, then it would highlight this. So the highlight just helps bring to your attention where your water limiting factor is, either your rooting depth or your probe depth, your moisture depth. And so in this situation, it is the root depth. And so this formula is set up to calculate your total available water content to the crop that's in that moisture. It is set up to determine which of these two values, either your probe depth or your root depth, is the smallest, and then so that way it'll calculate where your restriction of water is. So in this case, it notices through the formula that the rooting depth is smaller, so it'll use that number 2.5 feet, and up here in the formula tab times by 80%, because we know the probe probed that far, so that if the probe went through as we showed earlier, that means we'll probably have about 75 to 80% field capacity in that moisture. And then based off of our soil type, which is sandy clay loam, we can hold about 1.8 inches of water per foot. So it's going to take our rooting depth in feet times the amount of field capacity that's there, 80%, times the amount of total water holding capacity, 1.8 inches. And that is calculating we have 3.6 inches of water in the soil available to the crop. Now here is where it becomes key, and that is stress level. And stress level is 55% of field capacity, typically for cotton, is when you begin to have the onset of stress. That is not your permanent wilting point. That's going to be more 30-35%, but you want to avoid permanent wilting point. That's when you have had stress so severe the plant cannot recover even when adequate moisture is supplied back. So by then you've already had lots of yield limitation. So we want to shoot in this field to stay above 55% field capacity to try to minimize stress as much as possible. So right here, the formula is this. It's referencing back to our rooting depth, because that's how much area the plant is going to be pulling moisture from, times the water holding capacity of soil at field capacity, which is 1.8 inches for the sandy clay loam, or I'm sorry, just for the silty clay loam, and times 55% of that, because 55% of that total capacity of the soil is where we're going to see stress. And so it's saying if our cotton has 2.5 foot rooting depth, we're going to see a stress level when the soil water is below 2.475. So here we can see we have 3.6 inches of water available to the crop, so we are above our stress level, so we are okay. Now, days to stress. This is going to help us decide when we think we should start irrigating again. And the way this is calculated, I have it set up to where it takes the moisture we have now, which is right here, this total available water content, minus the stress level. So that's calculating how much moisture above our stress level do we have, and in this case it's about 1.125 inches, and then divides that by how much the ET for the crop is per day. So here is the estimated ET for the past week, is here in this cell, D14, and it is 0.245 inches per week. Now we want to know per day, so we'll divide that by 7. And then that value will be divided into the difference we have between our available water content and our stress level. So that'll tell us if we continue to evaporate at this average rate per day, then it'll take about 18.5 days for us to use all of this excess water, and then we'll reach our stress level. So at this current evapotranspiration rate, we'll reach the stress level in 18 days. So that shows that we have really good moisture, and we can probably hold off on the irrigation for a while. But that's only considering the evapotranspiration will remain a constant over the next week. So then, right here is the 7-day remaining soil moisture, and that's based off of we have 3.6 inches of moisture available now. If next week the crop in the next coming 7 days, if it has the same ET as the past week, so we just subtract this water content, we subtract the ET from it. So that's showing that in our next 7 days after the ET, we will still have 3.17 inches of water. So this right here, this calculates our irrigation demand, and that's just calculating the difference between our stress level and our available water content. And right now we're above stress level, so our irrigation demand is a negative. We do not need irrigation, so that's going to give us a green light. But say I changed, so let's say that everything's consistent except for our growth stage. We're all the way at max bloom now. Now max bloom, there's going to be a much greater water irrigation demand. The crop coefficient is 1.1 at that time. So that's going to change everything. Our water use jumped all the way up to 2 inches per day now. Our rooting depth at max bloom is, I'm going to say, our effective rooting depth is going to be probably 3.5 feet. And let's say we only have a 2.5 foot probe here, because it's been a lot more evapotranspiration, so we've lost a lot of our probe. And so here we've highlighted the probe now, because our probe depth is actually what our limiting layer is, and our available water content is 3.6. Our available water content is 3.6 inches in our rooting depth, or probe depth, and our stress level is 3.46. Because we have our stress levels increased because we have a larger rooting depth. So we are a lot closer to reaching our stress level. Days remaining to stress is 0.45. So then I'm going to say, okay, we need to go ahead and turn the pivot on and begin irrigating, because we are approaching extremely close to our stress level, and ideally we probably wanted to start irrigating a day or two before, because of our capacity. It takes us a week just to put an inch on. So that's kind of how I use this management tool. Let's say that we only have a 1.5 foot probe. Well then, see, we should have been irrigating 5-6 days ago, because we've already had stress here for 4.3 days. See, we're well below 2.16 inches available water. We're well below our stress level here. And and if we continue at this rate, we will almost have a completely dry soil in the next 7 days. So then you see our irrigation demand has become positive. Our demand is 1.3 inches. We can only put 1.1 inches on in a week, so we're already a week behind. So by this time, this is whenever you have had a poor irrigation management and you've really probably ruined your crop. And we have this red flag pop up anytime this number becomes positive. So it shows us we have irrigation demand. We need to be irrigating right now. And right here it tells us our demand is 1.3 inches. This calculates what type of irrigation length do we have to put out 1.3 inches. Well, if we can put out 1.11 inches in a week, it's going to take us 8.25 days to put out this 1.3 inches. And then down here is just something for us to kind of keep up with our capacity to irrigate compared to how much the crop is evapotranspirating, or basically how quickly can we replace the moisture that's being put in. So let's say we had no soil moisture, and so all of the moisture the crop was receiving was coming straight from our irrigation system. Well, we can put 1.11 inches on in a week, but this crop is using 2.12 inches in a week. So here it shows us that our potential to replace ET is only 52%. So once this number starts getting low, that's when we realize we're in a deficit irrigation situation, and we really need to try to stay ahead, keep our profile full, and try to stay ahead of the evaporative transpiration demand, because once that profile starts being depleted, we can't keep up because our capacity to irrigate is less than what the crop is actually using. And it shows us we're a negative inch of water use right here. So we're pretty far behind. So that shows we really should have banked our soil profile earlier in the season to help us out with this, to help us out once we are starting, our demand is greater than our capacity to irrigate. And so that's why I mentioned earlier, say we are here still just at the first square stage, and our crop coefficient is 0.22, or only 22% of this PET, and we're at a probe of 2 feet, or let's say 3 feet, and 2.5. That's our rooting depth. So see here, we have a moisture surplus. We have we can irrigate 260%, or 2.6 times more than the crop needs. And we know pretty soon, once we start blooming, our PET will be below 100%. We won't be able to keep up. So here, since we have a surplus, this is when we want to start increasing that soil profile by, we can put out 0.68 inches a week above what the crop is using. We're going to want to utilize that to our advantage to overwater above what the evapotranspiration is, just so we can increase our soil storage to have more of a profile, so there's more water so the crop can access when our irrigation cannot keep up with the evaporative transpiration demand. And so that's kind of how we manage our irrigation. So let's say we're at this stage right here, we're at first square. We have a 3-foot probe, which is definitely an adequate probe to irrigate our cotton at this, to keep our cotton going at this stage without irrigation. But I know based off of that crop water use curve that our demand is about to increase quite a bit when the crop starts flowering, and we won't be able to keep up with irrigation. We'll be in a deficit situation. So now I'm going to say, no, we want to keep that pivot on, even though our crop has adequate moisture, because we want to start increasing this profile so that we'll have enough irrigation there, enough soil moisture in there to help our crop out whenever the irrigation can't keep up. And also, right here you see the rooting depth is below the probe depth. Well, roots can't grow through dry soil, so we want to keep that try to keep that probe, no matter what, below the root depth until our roots are fully developed at max bloom stage, because we want to have that root encouraged to continue to dig down deeper into the soil, so that root will have access to as much moisture as possible when it is at peak water demand. Then over here, just some side things I have on here is just some agronomic data that you can reference while you are looking at your irrigation decisions. You can set up your fields here. I have our drip and our pivot, what our yield goals are, what our capacity to irrigate is in acre inches per day, the planting date, when is our max water use. So what I've done by max water use is here I've just taken the highest water demand stage of cotton, which would be max bloom, all the way to first open boll, which is 110% of reference ET. I've looked at the historical ET data of cotton, which I've posted in here. See, over here I've created just a historical file of here's the crop coefficient stage. So at each stage, what is the crop demand, and then here I've just multiplied that by our average ET for those months, so I can calculate. See, up here is the average ET per month for the total month. That's why they're so high. It's not weekly ET, it's the average monthly ET for the Lubbock area at this time of year. So right here, boll to first open boll and bloom to boll is when we're at our max crop coefficient or our max crop water use. And here is our here's our June, July, and August are whenever we're at the highest evaporative demands just based off of the climate. And so what it does is it divides this by 4 because that's monthly, and we want to know a weekly ET, and then it multiplies that by our crop coefficient. So our monthly, or it just leaves it, our crop coefficient times this monthly stage. So we know our monthly PET, or crop demand, is going to be 7.92 inches per month. And so our max demand is going to come in bloom to boll, and then our average precipitation is usually 2 inches in that month of August. So our irrigation demand to keep up is going to be 5.85 inches, and you divide that by the total months in August, or total days in August, which is 31. So our total daily water use is going to be 0.255 inches of water. So here that just shows you what your max water use is going to be, and then this shows you what is your capacity to irrigate max water use. Well, if we can irrigate 0.15 acre inches a day when we peak water use at a quarter inch a day, we can only keep up 62%. So that shows us we're at a 62% deficit. So that just kind of helps us keep thinking in the future. Eventually I'll reach a deficit situation, and also it just helps us keep in mind our yield goals. Then this, if you want to just have reference, you can put in your fertility requirements over here. Also over here it shows our irrigation deficit, and that's this again, our capacity to irrigate in a day reference to crop water use a day. So we can see our deficit months are July, August, and September. And so May and June, and May not so much because you don't want to flood the cotton out when it's so young and there's not much roots there already. And June is the last month you're going to have over capacity to irrigate. The only time you can build and bank soil moisture is going to be in May and June. So June is when we really want to focus on overwatering, as I mentioned earlier, and build our soil profile to help us through these months where we are in a deficit situation. Alright, so there you have it. That is the irrigation tool. This is all home built. I built myself, and it just shows you how you can use an Excel file, simple formula, simple math, there's no macros or anything in here, to help you determine irrigation management decisions based off of knowledge that you have of your crop, your environment here with your PET, and of your soil moisture, which we estimated in the field. So there you have it. I hope you enjoyed the presentation, and I hope this will help you in your irrigation management decisions in the future. Thank you.
And pray